Now, with that said, let's think a little bit about the modeling of the game of Battleship. Let's take a look. When we talk about a game, it's oftentimes that a game has a particular close relationship between the physical entities in the game and the entities that we model in our program, the things that we write classes about. So if we think about the game of Battleship, the physical entities we have are the board. It comes in that clamshell form. You flip it up. You have the opponents on one side and you have yours on one side. It has the ships. They're little plastic pieces with pegs in them that you situate in the board. It has the shots. They are white and red pegs that you put on each place that you try to shoot your enemy. Red if you hit and white if you miss, and that gives you a sense of where you've been so far. However, it's often the case that if we try to model the physical entities too directly, we'll find that we don't really gain any benefit. For example, if you think about it, in the game of Battleship, there's also an opponent. You want an opponent class. There's also the table on which you put the two boards. I guess that would be helpful to model if your friend really, really doesn't like how the game is going and wants to flip the table, so the table could have a flip method that ends the game. But setting all of those aside, we oftentimes need to think, what is worth modeling for the purposes of capturing the details of the program that we care about? And in some cases, we may eschew modeling the physical entities and instead model some of the abstract entities. Because even though in the game of Battleship there is a physical entity representing the shots, the white and red pegs, they do not represent the actions that somebody has taken. Because, for example, if you wanted to replay a game of Battleship, you don't just need to know where the pegs are on the board. You also need to know when they were placed. You have to know what the general strategy was and how it was that the pegs lined up the way that they did. There's more information to those actions than just the position of that peg. There's also what was the previous thing that happened, what was the next thing that happened, what was it in the sequencing, why was it that they placed that peg. There are many abstract entities that we might want to represent. And so we're going to try to model the game of Battleship. We're going to try to use object orientation in places where it is obvious that we need to use it, but we're going to try to avoid using a very heavy-handed approach in places where maybe we don't get enormous value out of a very heavy-handed class approach or an approach that really belabors the physical entities and the modeling of physical entities. Well, we could start in our modeling of the game of Battleship by thinking about the board. This is generally the starting point for the game. You place all of your pieces. And here you can see a simplified game with a 6x6 board. We have a carrier, a battleship, and a submarine. And it is our goal to turn this textual representation of the state of the board into a computational representation where we know at such and such location we have each ship, and at such and such location it's just empty water. So we might start off this game with, in fact, an object. And that object might be representation, or we might have a class here representing each ship with all of the shared behaviors, and then subclasses representing each type of ship so that we can print out customized messages. That is, the game is called Battleship, so maybe you want to print out a very special message when the thing that you've hit or when the thing that you've sunk is the battleship, so you can say, you've sunk my battleship. We can use some of the mechanisms afforded to us by the Python object model, like init subclass, to specify the details where each one of these ships differ from each other as part of the header line of these, as opposed to just having to add some fields or attributes into the body of this thing. So here you could see we could have an attribute, but that could be shadowed by some local instance state. Well, here we can just do it as part of the definition. So we have these three ships of different sizes with different symbols as are represented textually. And our init subclass allows us to capture all of those. So now the ship knows every ship that exists by symbol. And we can even write a class method to, given a symbol and its positions on the board, construct a ship. Well, from there, the code for parsing this board is actually fairly straightforward. We just need to iterate over the rows, iterate over each cell in each column, collect up each location, row number, and column number with each cell type, and then construct a ship from positions for each symbol and position that we see other than the dot representing open water. And when we do this, we can see our carrier, our submarine, and our battleship represented in this game. Well, we can go a little bit further than that, and we can say, part of the purpose of this game is not just to know where the ships are, but to know what state the ships are in. Have they been hit or not? So we could have another structure, a frozen set of each location that has been hit so far, and extend this slightly further. We may desire to make this code immutable, because we may discover that as part of what we want to capture in the modeling of this game was a strategy that fired in this particular order better than a strategy that fired in some other order. And in order to do that, we might want to capture every single snapshot of every single state of the game so that we can replay that, so that we can say, oh, once they hit in the top right corner, then it seems like their strategy said to go here. So if I wanted to put my ships in places that would counter that strategy, well, we could derive some counter strategies in that fashion. Because we're going to make this immutable, with this data class frozen equals true and the use of these frozen sets, well, it is the case that the ships do change state over the course of the game. They are hit. But we could make use of things like the replace method from the data class's module, and we could say whenever you fire at this thing, if you fired at a position that was not already hit, we'll replace this class, or replace the field of its class with its hits with that extra entry. Otherwise, it'll replace itself, which means if you fired and you fired wildly and you sent that into the with shot method of this class, it's just going to return itself. If you fired wildly, you didn't hit anything. Or if you fired on a space that you already hit, it's just going to return itself. Only if the actual state of the ship, if you hit some location that had not previously been hit, is affected, will it actually return a new object. And as a consequence, we can even start thinking a little bit about how this plays out when we play this game. Here you can see when we do a ships by name, submarine with shot, we can see ourselves missing the submarine on this line and actually hitting the submarine and getting a brand new object here. And this should be largely enough modeling for us to actually implement the core mechanics of the game. We'll write a very simple loop here to model just a very simple game where you randomly fire at locations until forever. Of course, we'll break after one step here, and here you can see we have all of the ships, and we can see that for that particular location, nothing is hit. So if we change our random seed very slightly, we might eventually see the first location it tries to hit will be one that is a successful location. It may take us a while, or we can remove this break and we can just see the game running forever. And do note that we don't store the new object resulting from this, so you can see that the ships are not accumulating hits. That's something that we have to do separately. Well, that's not altogether too difficult, and so if we wanted to, what we could do is every time we decide where we want to fire, we can just put it onto the ship, replace the ship object with the new one, and then just look for any ships where the positions have unhit locations to determine the terminating condition. And in fact, we could think that at this point, maybe it's worth structuring this code very slightly, putting some parts of this code in other places to support reusability. Note that even though the board is a dominant physical entity in the game, I do not have a modeling of the board here. And I don't seem to yet need to model the board. Here, the board really exists implicitly as a consequence of all the positions that are associated with the ship. But there is no actual modeling. There's no board class, no board object. When I think about the main loop of the game, I could decide to model that as an object. I could say, here's the main loop of the game, and it has methods corresponding to each action that you might take. But I may discover that one of the parallel modelings actually serves my purposes better. Instead of modeling the state of the game, the abstract entity representing all the things that you can do in the game, as an object, I'll represent it as a generator coroutine. And so here you can see I've moved some of the logic for constructing the game state from the raw board into this generator coroutine, where otherwise I might have moved it into the init method or the post-init method of a class or a data class. And I'll have the same loop that I had before, taking in all the locations which you want to fire at and updating some internal state based off of that. And so here you can see we try to see if that new shot would change the state of any of these ships. If it does, we update with the brand new ship. Otherwise, and we break out of the loop. Otherwise, we say there was no result and we yield again. And so with this very minor change, we actually should have a fully running game of Battleship. Here you can see we have hit all of those locations, and you can see where we've hit and where we have succeeded. Of course, we'll only run for 10 steps because there isn't a stopping condition just yet. Again, we only have one object here, and very light use of it, just this class here, this data class. But for the actual representation of the game, maybe we don't need that heavy-handed object-oriented approach. Maybe a closure, or maybe, in this case, a generator coroutine would work.
Thanks for watching. If you enjoyed this video, give it a like, hit subscribe, and check out the recommended video on the screen. See you in the next one.